Good morning or afternoon, depends on where you are. Welcome to our webcast today, focusing on solving thermal issues in electronics design. My name is Andy Deal. I'm your host, and we're very fortunate to have an outstanding guest speaker, Richard Ozaki from Mentor Graphics, with us today. But before we pass the presentation over to Richard, I'd like to spend a couple minutes talking about Saratech and sharing some information with you. So for over 15 years, Saratech has been helping companies solve product development challenges by helping customers optimize their processes across design, analysis, manufacturing, and quality systems. We're the industry leader in the PLM space through our partnership with Siemens PLM software, but we also partner with companies like Mentor Graphics to provide our customers with top-notch product development solutions. We're headquartered in Orange County, California, and our team of professionals are located all across the country. But before I pass the presentation over to Richard, I would want to remind everyone that if you have a question at any time during the webcast, go ahead and type it into the chat panel, and we'll address your question in the Q&A portion. Also, when you log off the webcast, there's a short 5-question survey that pops up. If you wouldn't mind, just please take a couple minutes to fill that out and give us your thoughts. With that, I would like to now pass the presentation over to Richard Ozaki.
Thank you very much, Andy. So thank you for the introduction. My name's Richard Ozaki. I work for Mentor Graphics, and I'm a technical specialist, and I've been specializing in our CFD tools since 2008. I have a Master's of Engineering in Mechanical Engineering, and I specialized in CFD analysis for turbo machinery. These days, working at Mentor, I specialize in thermal analysis for electronic systems, specifically PCB level thermal analysis. I'm based out of the Bay Area, San Jose, California, but cover all of the US. So a little bit about Mentor Graphics first of all. Mentor Graphics is a large EDA, electronics design automation software company. It specializes in software for developing silicon and PCB design. Okay, as of November 2016, we were acquired by Siemens PLM, so we have a tight integration with Siemens and also our partner Saratech. About 5,500 employees globally, and at the moment Mentor Graphics is headquartered out of Portland, Oregon. Okay, I work for a smaller division within Mentor Graphics called the Mechanical Analysis Division, and we specialize in thermal analysis software and hardware for the electronics industry. So what is CFD technology? Well, CFD stands for Computational Fluid Dynamics, and it's the mathematical prediction of fluid flow and heat transfer. You can see some of the pictures on the screen here. You can use it in any application where you've got basically fluid flow or heat transfer. So in the top right you've got things like electronics where components will get hot and you need to use air to cool them. You might want to optimize things like heat sinks or guide the airflow with baffles. But it can also be used for something like automotive applications, so exhaust systems, making sure that you've got the right flow rates and the pressure drops in your airflow design. And also not just airflow but also liquid flows, so things like pumps, valves, turbines, anywhere again where you've got that fluid flow and the heat transfer. Now just a little bit about FlowEFD, just a few of the key features that I want you to look out for. It is seamlessly integrated within major CAD systems, two of which that we support is the Siemens PLM tools, Siemens NX and Siemens Solid Edge. So we sit directly within the CAD system, and the benefit of that is there's no translation, there's no exporting data, you're not having to you know, work with dumb imported geometry and SAT and step files, and that really means that you get access to all the parametric CAD definition, how the CAD's been built, and that's got a lot of benefits when it comes to optimizing your design. So we're integrated within the CAD system. Another one that we're going to be talking a little bit about is our immersed boundary meshing. So we have some really advanced meshing technology in Flow EFD. Again, I'll be showing you during the demonstration, but overlapping geometry is not a problem. Manual meshing time is reduced, and it's really designed to be a non-expert tool for CAD designers to use. Okay, and meshing, automatic meshing is a big part of that. Turbulence modeling is also something that we handle very, very nicely. We've got a full laminar, transitional, and fully turbulent flow regime model within Flow EFD. And again, it's largely automatic, so you don't really need to know what sort of flow is going to be happening inside of your electronics. Is it going to be natural convection? Is it going to be forced convection? Are you going to get boundary layer growth in the fins of your heatsink, for example? So you really don't have to be an expert to use our tool. The modified wall function captures boundary layers within your simulation with very high accuracy and very low grid count at the wall. Okay, so the real benefit here is you don't have to worry about generating a very fine near wall mesh. Again, the software will take care of that for you and give you the correct accurate flow profile and the pressure drops within your system without that expert CFD or flow knowledge that a lot of other tools require you to have. And then finally, we have the parametric study variant analysis, and this is really a virtue of being inside of the CAD system. You can take advantage of part families, assembly families, you can change any of the parametric CAD dimensions, and then the software will automatically recognize that and then update the CFD analysis. So this makes it really easy to quantify differences between your various configurations in NX or Solid Edge, right? So you can just tag on a Flow EFD analysis onto different part families and hit run, and you can quickly see the differences between your various part family members. Okay, and that allows you to do what-if simulations and optimization before you commit to tooling or prototyping. So that was just a very brief overview of what we're going to be looking at. I want to spend most of the time actually looking at the software itself, so we'll do that right now. So I'm using NX 10.0 at the moment. We support all the way back to 7 and all the way forwards to 11. Okay, and you can see this is the actual NX window. If I go to Help and About NX, this was 10.0.3.5, for example. And the way we start Flow EFD is under the File, All Applications. You'll notice we have a Flow EFD simulation option here. So let me start that up, and that's going to start my Flow EFD analysis. And you can see that we have this extra Flow Analysis tab up here. Now, first of all, I want to show you some of the capabilities we have with respect to importing EDA data. Apologies, let me just save this and import the data. And what we work with is something called an ODB++ file, and this is the preferred method for importing PCBs. We also have the ability to import IDF and also Native Expedition, which is a Mentor Graphics tool. But ODB++ is like a neutral file format, like the step file for a PCB, okay? And this has all the information we need for actually creating and modeling that PCB, right? So, for example, here's my board. It has all the layer definitions, like all the traces, the vias. So if I click on the dielectric layer, you can see the vias that stitch the layers together. I can have a look at the ground plane or the power plane. So this is a 6-layer board. It's come through with the correct thicknesses and the percentage coverages. So that's given me my board in very high detail. I can do things like filter out components. So if I don't want certain large components, let's say I want to filter anything less than 12 millimeters, then I can turn that off and that will remove some of the components for me. Right? So I can do component filtering. If I wished, I can actually do full trace modeling. So I can model things like traces in the model, such as, let's just choose some of our data lines here. I can choose to have these specific nets in the modeled explicitly. So let's just select these nets, change that to explicit, and change the modeling level to explicit. And what that's going to do is, if I now transfer that over to Flow EFD, that will create the 3D geometry of that particular board for me over in NX for me. So it's actually creating the structure for me now, and if I look, you can see here's my PCB. If I go into wireframe mode, you'll see some of those nets that I selected. It's actually created the 3D geometry of the detailed copper for me. So if I go to make displayed part and zoom in here, hopefully that's not coming across too jagged, but you can see it's actually created the 3D geometry of the copper for me. So if you want to go to this level of resolution, FlowEFD can do that for you, and we have various modules for importing detailed PCBs. Okay, so that's how we do a board, and let's have a look at more of a system level analysis. So what we have here is that same board. I've placed it inside of my my casing with some vent holes on the side. I've got a fan on the inside as well, which is going to be drawing air through the system and cooling down my electronics. So this is my first proposed design for my electronics enclosure. And you can see I've taken a guess at the heatsink, taken a guess at where the fan should be, I've taken a guess where the vent holes should be and how many there should be. I don't know until I actually physically test this whether this is going to work. And this is what FlowEFD and CFD simulation of electronics will allow you to understand before prototyping, before manufacturing, before you commit to tooling. So let's start a FlowEFD analysis and let's have a look at some of the options available. Okay, and we're going to do that by running through the FlowEFD wizard first of all and creating a project. Let's just call this Saratech 1, for example. Okay, we choose our unit system. For example, let's make my temperature into Fahrenheit. And then we choose our analysis type. Now, because there's no defined inlets and outlets in this model, this is going to be an external analysis. If I sealed up all these holes, that could be internal. But for now, we're just going to run this as an external. I'm interested in heat conduction of solids. That's going to be flow and heat transfer. Okay, I can set gravitational direction for my for natural convection purposes. I just need to change the direction to the Z direction like this. Okay, and you can see gravity going to be acting in that direction. Okay, so these are the features I'm going to turn on for now. My working fluid is going to be air, so I double-click that and put that into our project. And my default solid, let's choose aluminum for our solid, for example. Okay, and then here's my ambient conditions. So this is atmospheric pressure at sea level, and 68 Fahrenheit, that's kind of a nice pleasant day outside, but for a worst case scenario, let's choose something a little bit warmer at 120 degrees Fahrenheit. And what happens when I click finish is that we'll get a black box around the geometry, and this is going to be our computational domain. So everything inside of this volume we're going to be solving for in terms of the fluid flow and the heat transfer. Now it's a little bit big at the moment, so I'm going to make that smaller. Let's just view from the side, for example, and let's just grab my computational domain and tighten that up on the geometry a little bit. We don't need to simulate that much, so we're just going to make that a little bit tighter. And if we view from the top as well, I'll zoom out and just grab my computational domain and put it around the geometry like so. You just need enough sort of computational domain to capture the main flow regime around my electronics box. And then we can do things like assign materials. So at the moment everything is assumed to be aluminum that we ran through in the wizard. But say that we let's say that we want to hide the heatsink. I've got a thermal interface material, like a gap pad between my heatsink and my chip, and I can assign a material onto that. Okay, right-click, insert a solid material, or I can come up here to my ribbon toolbar and insert a material, and let's come back to our tree over here. It's brought back that part for some reason. But I can select it on the screen. Yep, you can see that I've got my TIM in here, thermal interface material, and I'm going to choose my thermal tape material. And you can see now in my FlowEFD tree, that's assumed to be my gap pad over there. And I can do the same thing for my fan. Right? I can choose my fan parts, just click on the screen, go to predefined, and come down in here and find my polycarbonate, hit OK. And you can see now I've got my two materials in here. And like this, FlowEFD, we can start to assign all the various boundary conditions that we're going to be using for our analysis. Now what I'm going to do is just kind of skip to a project that I've already pre-built, but you can see I've got aluminum on there, I've got polycarbonate, I've got my thermal interface material. I have my fan on here. Okay, so a fan is basically going to be a flow generation device where I've got two faces selected, and these are going to be linked together with a fan curve. So a fan curve is something that you can get from a manufacturer, and that will basically define what the flow rate is going to be based on the delta P across that fan. Okay, and this is something you can just pull from a data sheet and store in the FlowEFD library. We do have a large library of manufacturer fans built into the software. So for example, I can choose a Pabst or EBM, although they are the same company now, Sunon fans, Sanyo Denki. So we do have a large variety of typical electronics cooling type fans in our library. We can also generate some heat on our board. So for example, this guy is going to be generating 1.1 watts. These guys in total have 1 watt in total, okay, spread over these 7 components. My RAM modules are dissipating 3.6 in total, okay, and these guys down here are generating 2 watts. Now, if you have information on specific components that you would like to model in slightly higher fidelity, then we can use something called a 2-resistor component. So a 2-resistor component assumes that you've got heat dissipation down into the board and up into the case. So there is a thermal resistance in those 2 directions. And again, this is the sort of data you can grab from data sheets. So you've got the junction to case and junction to board thermal resistance, which you can define and store in the FlowEFD engineering database. Okay, and then we have my PCB. Now, when I earlier imported that part into NX, this is actually just the geometry inside the model. There's no material definition. So over here, we need to assign a material onto here, and that's done using a PCB smart part. And the PCB smart part, you can select the number of layers, you can give it a rough percentage coverage of copper on those layers, and it will create an effective material for that PCB. So this is useful for when you've got things like angled PCBs or PCBs not aligned to the global coordinate system. This is particularly useful, and it will make sure that you've got the correct in-plane and through-plane thermal conductivity within your model itself. Now, just a quick note on solving this model. There is some meshing involved. We'll talk about that when we look at the results. And then the actual solve process. So CFD is an iterative process. It takes a little bit of time. This particular model takes about 20 minutes or so to solve. Right? So that's doing the flow and the heat transfer. And it's very numerically intensive on the CPU. So you can utilize as many cores as you wish, and that's by default. There's no additional cost there to actually utilize all that horsepower on your machine. So let's have a quick look at the sorts of results that we can get. Okay, so I'm just going to show my results. So here we're looking at a computational mesh and a plot of temperature in the model. Let's just go normal to the screen. We can see how FlowEFD deals with the mesh. So in the far field we have these large grid cells, okay, they're Cartesian in nature, but as we get towards some of the more critical smaller features in the model, you'll notice that the grid cells get smaller and smaller, and that's done using octree meshing. So you'll see that we take a single grid cell, okay, we split that into 4, right, and then 4 again, 4 again, 4 again, and what that does is it maintains the aspect ratio of the cell. So the aspect ratio of this is exactly the same as the large one, and it also maintains the growth ratio. So you're going from always 2 to 1, 2 to 1, 2 to 1. So you're going to get a very robust mesh and a very robust solution from this Cartesian meshing schema. Okay, so you can see here, here's my cut plot. Let me just come in here and turn off the mesh for now. We're still going to just look at the temperature, and let's just look at our model in wireframe. And what I can do is, if I hit play, this cut plot can move throughout the model, and it will give me the temperature at various locations within my electronics enclosure. And you can see, you know, as it cuts through the board, we're going to get a high temperature there. Let me just stop that and actually pull that down. So let's go turn on my preview. and pull that down through my board itself. I believe it's 0.5 millimeters. Let's just go OK on there. Okay, and you can see now the sorts of temperatures that we're going to be getting. We can probe the model and understand what sort of temperature that we're going to be getting on the various components in the model. If I wanted to, I could also have a look at the velocity. So how fast is the airflow moving through my system? Right, so you can see around my fan. Let's just auto-arrange that real quick. Okay, around my fan I've got very high velocity of air. Around these slots in the side I've got these high velocities. So we can have a look at velocities, temperatures. I can even look at things like pressures within the system, right? So what's the typical pressure drop across the system there? I can have a look at the final steady state temperature. So here's my PCB temperature. You can see a hotspot under the RAM module there. You can see my heatsink temperature. You can see my 2 resistor model under there. So we can have a look at the temperatures in the model. And remember, we're not leaving NX. We're still fully within NX at the moment, and we're able to perform a thermal analysis and understand what the airflows and the temperatures within the model are going to look like. So there we have the airflow as well, and this will allow you to see where dead zones in the model are going to be, where any recirculation might be, if the flow is bypassing the heatsink, right? So you're not seeing too much flow going through the heatsink. That might not be a great design. So this is the sort of things that the software can tell you about your electronics thermal performance. Okay, and then we can get some numerical information from the software. So let me just actually, let's leave this guy on and turn off my flow trajectories. So how hot are all the components getting? Well, we can have a look by plotting the results. So you can see my main 2R components getting up to about 87 degrees C, right? And my RAM chips are getting up to, you know, between 78 and 75, and my coolest chip over here is at 68. That's well below the maximum allowable junction temperature in the model. So we're fine at the moment. But you know, fine, we can do better than fine. So we can actually start to optimize this model a little bit. So as I mentioned, because we're embedded within NX, we can take advantage of various parametric features within the model. So if I wanted to understand where the best position for this particular fan is going to be, I can do that using NX configurations or part families. So here's my, let's have a look at project 2, for example. So you can see the fan's going to move along to a new position within my electronics enclosure, so that's moved along very slightly. If I look at project 3, again you'll see that this fan moves along very slightly to the next position. And then finally, project number 4, we'll see the fan in the final position. So this is all driven using NX, and what I found was that project number 3 actually gives me the best optimum heat transfer, and as you might expect, it's directly in front of the heatsink because that's going to be forcing the most air through my heatsink. So if we now have a look at what the airflow looks like, you can see I've got a lot more flow going through my heatsink. The flow inside the model is very slightly different. If I plot the temperatures on here as well, you can now see that my RAM chips are slightly hotter and my main chip is actually slightly cooler. So if we have a look at the temperatures now and just quickly have a look, you can see I've gone down from about 87 to about 75, okay, and all the other components are cooler as well. So having your electronics run cooler are going to give you a more reliable design and then possibly reduced field failures and warranty costs. Okay, so if we wanted to, we can even go as far as to go to, where are we? Just a moment, results, geometry, results, compare. Okay, so I can compare the different models. So if I wanted to compare the goal plots across my various different projects, these guys, I can hit compare, and what that's going to do is it's going to pull the information from all 4 of the projects that I've got, remember the 4 different fan positions, and then give me the results all in one place. So you can see now, let's have a look. So my 2R component in project 1 was at 87, right? So you can see the various temperatures of the different projects. So project 3, 1, 2, and 4. Okay, and we can see the deltas between the projects. So, you know, project 1 was, I'm getting a delta of 12 degrees C, so I'm cooler by 12 degrees C just by moving that fan an inch to the right. Right, so these are the sorts of things that you can quantify and understand before you commit to manufacturing. So just before I finish, I just wanted to quickly show you some of the direct results. So here you can see the fan on the far left. As you can see, it's starting to move across to the right. And if you look at, keep an eye on the legend over here. I fixed it between 35 and 90. Right, so it's moving across, and you can see the main chip is yellow, and then it starts to get hotter again as it moves past the most optimum position. So again, this is just intelligently designing your airflow and your heat transfer for your electronics. Okay, and then we can see our final proposed design. And I should mention, it's not just one parameter that we can change. You can create a huge family table, part family table in NX, and just tag on a FlowEFD project onto each one of those. Simply update and run, and it will maintain all the same settings, all the same solution parameters, all the same results parameters. You can just do that compare between all the various projects. So in summary, why do we even perform thermal analysis? Well, there's three main ROI points, as I've kind of been hitting home here today. One of them, the most obvious one, is reliability. Right? If your optimized product runs cooler, you're going to have reduced failures. You're going to have reduced warranty claims and fixes for your model. You're also going to have reduced design costs, right? So there isn't as many respins to get your product right. And reduced respins means reduced prototyping costs. You're not sending off tooling or prototyping manufacturing costs by getting the design right. You're doing maybe 2 prototype runs rather than 10 or 15. And then finally, reduce design time. So again, this is linked to the one before, but if you're doing less prototyping and testing, then you're going to reduce your lab costs, and you're also going to be faster to market. So that's really kind of the ROI of why people perform electronics flow and thermal analysis, to understand how their product's going to perform, and you can recoup your money, the cost of the software, by looking at these ROI points. So that was a very brief overview of FlowEFD. I think we're at 11:28. So what I'm going to do now is, or Andy, if you could maybe open up the lines for a Q&A session, and if you could tell me some of the questions that have been typed into the question box.
Okay, very good. Thanks, Richard. That was a very detailed demo for the amount of time that you have. So at this point, please go ahead and type into your chat box any questions that you have for Richard. And also, I do want to remind the audience that while we're waiting for questions to come in, that when you log off, there's a short questionnaire. Please take a couple minutes to answer that to help us out. One question that came in from Doug: does FlowEFD address water cooling integration?
Yes, absolutely. So you can have multiple fluids within the model. So if you wanted to model a cold plate, for example, you can create a fluid subdomain part, specify the internal cavity where water is going to be flowing, and then you'll have the correct flow parameters for water glycol or something like that within your cold plate. So yes, absolutely.
All right. Another question that came in from Eric. He wanted you to talk a little bit more about solid meshing. Was there something specific about that, Eric, that you want to learn, or in general?
Well, I can just kind of touch on that very briefly. So FlowEFD actually meshes the solid and the fluid all together in one hit. So if I just quickly, I know we don't have too much time, but let me just quickly touch on how we mesh. Oh, let me just go normal to the screen. All right, so let me just hide all the geometry as well. And so what the software does is, if you zoom in and apologies, let me just hide this one. If you zoom in, what you get is these partial grid cells. So we don't mesh solids and fluids separately. We have a partial cell algorithm where we take a single grid cell and internally we'll split that between solid and fluid regions. And partial cells can have multiple control volumes, as we call them, within the cell itself. So this is where we apply our boundary layer and convective heat transfer on this planar surface, on this interface between the fluid and solid. And this is really the secret sauce behind FlowEFD, is our partial cell technology, which allows you to have this coarse grid cell at the wall whilst maintaining the correct and accurate flow and heat transfer characteristics. So we have white papers on this. If you're interested, contact this email address and someone will get you the technical documentation you want.
Yeah, absolutely. If you have any other questions, or you need to see a more specific demonstration, absolutely please contact us, and we'll be more than happy to help. At this time, I don't think we have any more questions, Richard. So once again, I'd like to thank everyone for joining us today. Just a reminder that all of our webinars are recorded. So if you want to go ahead and subscribe to our YouTube channel, you get notified whenever these recordings are uploaded. Oh, hey, we look like we have one last question that came in here, Richard.
Sure.
From, I hope I pronounced your name right, Felipe. Is FlowEFD capable of modeling gas that consists composition? I'm not sure what that means.
I think the question is related to multiple species within the model. So the answer is yes. So when you come to specify which gases you're using, you can certainly mix gases, right? So you can put in you can put in as many gases as you wish, and then you can specify the concentration, either a mass or a volume fraction, between the two gases. So you can create different species. We can even go as far as doing combustion, right? So if you wanted to look at combustible mixtures like methane and air, or other gaseous fuels, we can look at combustion and chemical reactions that way as well.
All right. Thank you so much. And just as a reminder, in 30 minutes, we try to give you some quick overview. Again, contact us if you have more specific questions that you'd like to have answered. With that, I would like to thank everyone for joining us today, and hopefully we'll see you soon on the next webcast. Thanks, everybody. Thank you, Richard.
Thank you, everyone. Goodbye.